Welcome to this lectures on linear algebra. In the last lecture we have seen the use of elementary matrices to reduce arbitrary matrix of rank R into a diagonal matrix. So let me repeat a statement what we proved last time, and then we will improve this. So theorem what we proved last time. So A be a matrix with entries in a field M cross N matrix. Of rank R. Let me remind you also, we have proved that the rank of a matrix is the dimension of the column space of the matrix, also equal to the dimension of the row space of a matrix. Rank R, and let us put K to be the minimum of M and N. Okay, then there exist elementary matrices B1 to BP, and this will be of order M. Square matrices, elementary matrices are always square matrices. Elementary matrices B1 to BP of the square matrices of order M, and a C1 to CQ of square matrices of order N, such that when you multiply A by pre-multiplying by B1 to BP, this means we are making the row operations on the matrix A corresponding to these elementary matrices, and when I multiply by post by C1 to CQ, that means I am making elementary or column operations on the matrix A according to these elementary matrices, and then you get a diagonal matrix D. This is the diagonal matrix dag A1 to D1 to dk, which is in M, M, N, K. This notation is that D1 to dk is on the main diagonal of the matrix, and the remaining entries are 0. And also we can also, where we can even choose, we may even choose D2 onwards till R to be 1, and remaining diagonal are 0. And in the case of a square matrix, so if full rank case, that is R equal to N case, this C1 to CQ are not necessary. Then C1 to CQ are not necessary. This is what we proved last time, and this D1 is it actually will be it is related to determinant. When it comes, I will say it that time. Now I want to do it a little bit even better. So the next thing I want to prove is the following thing. This theorem is also known as, some people call it LR decomposition. So there is, before I go on, I just wanted to say that the earlier theorem, this will also allow us to compute the, if one want to compute the inverse from here, that will also allow us to compute inverse, because we know inverse of a diagonal matrix, we also know inverse of a elementary matrices. So this, when you rewrite it, this will go A equal to, I will multiply from this side by this inverses of B1, B2, BP 1 by 1. So this will write as T here, and then you multiply 1 by 1 B1 inverse first, then B2 inverse, etc., BP inverse, and this side is first CQ inverse, C1 inverse. So A will have a representation between representation as a product of elementary and diagonal matrix, and this will also allow us to compute the inverse of A. If A is a square matrix, then you can just compute the inverse on the right side, and that is the easy way to compute the inverse. Not only that, this also proves in a square matrices case that these elementary matrices along with the diagonal matrix, they generate all matrices. So this I will say it when I talk about group theoretic properties of the GLN. So the next theorem now again, let A belonging to MMNK rank R, then there exist normalize low triangular matrix. L in MMK. Recall, normalized low triangular, you know, that means only the below the main diagonal entries can be 0, above main diagonal entries are all 0, and normalized means on the main diagonal the entries are all 1, and an upper triangular matrix normalize again. Don't need upper triangular to be normalized. Upper triangular matrix, what do I call it, R, which is in MNK of rank R, and permutation matrices remember the notation for the permutation matrices as P suffix sigma, where sigma is a permutation, and this is in PMMK. Sigma should be a permutation on M letters, and P phi is a permutation matrix of order n, where phi is a permutation on n letters, such that the given matrix A, when I multiply P by P sigma, which makes sense because the order is correct here, note that orders are correct, so this product makes sense. Similarly, I can multiply on the post by P phi, this is equal to L times R. So some people, some authors also call this as a LR decomposition. Of A. Which is also related to popularly known as singular value decomposition of a matrix. I will, when I have enough vocabulary to deal with that, I will say it, but this is essentially for that. So if R equal to n, that means rank is full rank, then one can forego the matrix P phi, as in the earlier theorem case. See, you do not need this matrix then, because you can manage with alone the row operations. This means, and R can be written as a product of diagonal matrix in D in GLMK and a normalize upper triangular matrix R prime in M N K and obtain P sigma times A equal to L, and then R, the original was R, that we have written it as a diagonal D times R prime, and this R prime is upper triangular matrix. So therefore the statement is, from a given matrix A, by applying permuting the rows, we can arrive at lower triangular normalized matrix, D diagonal matrix, and R normalized upper triangular matrix, and all these products make sense, the orders correctly. Okay. So the proof is again reviewing the proof of the earlier theorem. So all that one has to do is, one has to be only careful about what operations we are using. So proof, I only want to review the operations on the matrix A we want to do, either row or column. When do they occur with the permutations, and not the elementary matrices of type one row adding it to the a multiple of one row adding it to the other row. These are the most important for us. So review the proof of earlier theorem. So what do you want to review? Where I want to review where exactly is necessary to use interchange of columns and rows. Okay. So, you remember when we in the proof of the earlier theorem, when we have matrix A, we have changed it to the matrix R, and R has the form, I will write that form, R has the form something on the diagonal C11, C22, CRR, below everything is 0, this part is also 0, below this everything is 0, and these are some entries. These are some could be non-zero entries in the field. This we can make it only with the row operations. Let us see how did we do it. So, first we made the top entry to be non-zero. That is where you will need possibility to interchange the rows and columns, and then once you have done that, then all below that you can make 0. Similarly, C2 and so on. So to understand exactly, that means I have to do this for j equal to 1 to r. So, suppose we have done it for up to some j, and what do we do after that? So, that means if you have done up to here, then after that, below that we want to make all the entries 0. Once you bring one entry to be non-zero, and then after that you have to bring all the entries to be 0. And that, for doing that, we are going to multiply only the row operations. That means we are going to pre-multiply the A with the matrix Bij's, Bj. So we are applying this B, I, J, A, these matrices, where A is a scalar and I is later row. So I is bigger than J. So therefore these matrices are already normalized and low triangular. These are normalized and low triangular. So we have to multiply by A on this side, and maybe the permutation matrix. But what I want to analyze now, I want to interchange these operations. So that means whenever I need a permutation matrix after this, that means if I have to multiply this operation further by interchanging the rows, so 2 rows P Ts and times B I J A. This we have to multiply from the left to the A. If I could interchange this, if I manage that these are interchange these operations, then what will happen? Then these A, these all together I will absorb those permutation matrices corresponding to the transpositions in the big permutation matrix, and the before this elementary matrix will come, but because they are normalized low triangular, I will take their inverses and will get here. So that will become L. So we need to only to analyze that what happens to this. Can I write this as the product the other way? So B somebody, B, what will I call it? B T, not T. I need now many letters. B K L A times some other permutation matrix, P something, PQ. If I can manage this, I have to analyze this. If it manage, then I will, this L will get the inverse of all these product elementary matrices, and the inverse of a low triangular is also low triangular. normalize also will remain, and I will shift this to the other side and I will get L that way, and these P, these are the corresponding to the transposition, they will all collect together and that will become the permutation matrix. So, I only have to note this. So, what are the assumptions on the indices A and J here? Let us review. That means this index I is bigger than J first, and these two indices T and S, both are bigger than J, because only later rows we have interchange. So, these are the assumptions. Now, we want to therefore analyze this product. So, now there can be two cases. These I either belong to T comma S, not belong to, or it is one of them, or without loss I will assume I equal to T, because if it is one of them, then this matrix I can PTS is also PST. So, I can without loss I can assume it is the first index T or first index T. So, in this case what happens to this product, let us compute. So, PST times BIJA, just put the definition of BIJA, that is PST times identity matrix plus A times the matrix units EIJ. And now you just multiply it out. This is PST and I am taking this case. So, this I has nothing to do with the T and S, and also J has nothing to do with T and S because both indices are bigger than J. So, this interchanging will not disturb this. So, this is same as A EIJ, because multiplying this is like interchanging the Sth and T row. So, this is same as saying BIJA times PST. There is a little bit thing to check here, this equality, but that is more or less obvious. So, this means directly this matrix PRS will commute with this in this case. So, therefore, I will just interchange their order and then go on. In this case PST times BI is now T. So, I will write T here, TJA, but this is same as PST into again EI E capital I, this is identity matrix, plus A E I is T, TJ, but this is equal to PRS PST plus now A times this, now T is a common. So, this will become no, I wrote the other way, this I wrote, this I wrote TS, this is TS. Of course, it is ST also, but I want to write TS. This is TS, and then plus A times E TJ, but this is same as BIJA B, I am getting confused. So, this is not BT, this is BS, because S and I change. No, this is correct. B, T J A times P T S. So, it also commutes. This is B T S, this is S. So, they commute. So, I will make bring them on one side and then we are done, because then we can write all collectively these permutation matrices absorbed here and multiply by the inverse of those elementary matrices and get this lower triangular matrix. So, this is R and then we are multiplying this side by this. So, now after this we have to make the diagonal and so on. So, that was the same procedure as earlier. And similarly for R equal to n case we can carry on the same operation. Okay. So, all these details, see it is a bit computational to do it, but one has to do it once, and all these I will write precisely in the notes, so that even if there are some little errors here you can check there. Okay. All right, now I want to discuss what is known as elementary divisor theorem. This is very important. Elementary divisor theorem. And I will give two applications of this, one in a theory of finitely generated abelian groups and the other will be in number theory, solving systems of linear Diophantine equations. Both are of very important for many kinds of many scientists and many engineers, especially solving Diophantine equations. Okay. So, that means we are dealing with now not the field. So, I want to replace a field by a nice ring, so commutative ring. So, Z integers, that will give us applications to the solving linear Diophantine equations, or also I will replace it by a polynomial ring over a field in one variable kx. This is a polynomial ring over a field k in one variable x, or also I will replace by a power series ring in one variable over a field. This is a power series ring, formal power series ring. Or more generally you can consider these are very special cases of the class of commutative rings called Euclidean domains. A. This all we have seen that this ring of integers is Euclidean domain with in fact the usual division algorithm will give you the Euclidean function. Here also the same, only thing integers are replaced by polynomials and the degree will give the Euclidean, and here it is even better. So, this is all these rings are very important. This is study for number theory, this is study for algebraic geometry or polynomial C in general. This is also local analytic geometry will be the power series ring. Okay, so what are we considering? We are considering matrices over this. For example, I will stick to this, and a similar thing you can do it for all other rings, replacing division algorithm in general by Euclidean functions. So we are considering a matrices M, N, Z. These matrices also you can think as group homomorphisms from the group Z power N to Z power M. Group homomorphisms of additive groups. See, this is a direct sum of or direct product of Z n times. This is a direct product of M Z m times, n times, and this is a direct product of Z m times. And these modules, these have the basis. These are the standard basis. So these are actually free Z modules. So all the time we were using that vector space as a basis that they are given here for such rings. So either you think this or think matrices. That is equivalent. The same proof. Each matrix will give you a homomorphism, and each homomorphism will give you a matrix. The homomorphisms from Z power n to any group will be uniquely determined by its values on a standard basis, and those you write in terms of the standard basis with coefficient, and those coefficients will give you this matrix. The same. Okay, so this is group. This is a group under matrix addition, under addition of matrices. That is under component wise addition, and therefore it is a Z module under again component wise scalar multiplication. So it's not a subring, it's not an algebra, but this is, you can think of this is a subgroup of M, N, Q, where Q is the field of rational numbers, which is the quotient field of Z. And so this is a subgroup, this one is a subgroup. And if you take square matrices M equal to N, then actually it is a subring, because then you can multiply matrices, and with that it is a subring. That means what I am saying is, if I have two square matrices and if I with integer entries, and if I multiply them, you get again a square matrix with integer entries. That means it is a subring. Okay. And therefore, when I consider a matrices with integer entries, I can also consider them as a matrices with rational entries, where now I will apply our theory for the field case, because Q is a field, and therefore what is more important now, what remark I want to make is, if I have a matrix A with integer entries, then rank of A makes sense when you consider A as actually an element in M, N, Q, because we have studied over a field, rank makes sense. So when I have a matrix here, I will think it is a matrix here, and rank will make sense, and that this rank is well defined. An integer, and so that is what it is, that is the number of Q linearly independent rows, or also equivalently number of Q linearly independent columns. But you see, Z linearly independent and Q linearly independent are closely related. So that is the rank I will keep saying. Okay. So that is, this rank is also nothing but the dimension over Q as a column space of A, which is also same as the row space and so. So, we will make a break and then we will continue after a while. Thank you.